Welcome to this video. A company launches a new machine learning model. 3 days later, the dashboard shows plus 12% uplift. And as you can imagine, everyone gets very excited. But then someone asks, wait, is this actually real? And suddenly the entire room goes silent. What exactly is statistical significance? What is a p-value? How does a t-test decide whether an improvement is real or just random noise? Why do confidence intervals shrink over time? How do companies decide sample size before running an experiment? What are false positives and false negatives? Why can checking your A/B test too often completely invalidate the results? How do Google, Netflix, and Amazon safely deploy changes to millions of users? And what happens when A/B testing isn't even possible? In this video, we'll break down the core ideas behind A/B testing completely intuitively. From experiment design and splitting strategies to uplift monitoring, simulated experiments, statistical testing, reporting results, and the real reason so many experiments fail. Are you ready? Let's go! A/B testing is a powerhouse tool in tech, marketing, and machine learning. It's the gold standard for causal inference, helping us answer one critical question. Did our change actually cause the improvement? Imagine you deploy a new model and metrics improve. Great, but did the model cause it? Maybe traffic spiked, a holiday hit, or user behavior just shifted. You could be fooling yourself. That's why A/B testing exists. Instead of a full rollout, we split users into two groups, a control group with the old system and a treatment group with the new one. This isolates the actual effect of your change while controlling for external factors. It's also safer. If something breaks, only a small fraction of users are affected. That's the core idea, not just measuring results, but proving your change caused them. Every A/B test starts with a hypothesis, and this is where most people already make mistakes right at the beginning. A hypothesis is basically a structured prediction. It looks something like this. Structure of a prediction. If we do action A, we expect metric M to improve by X% because of research, past experiments, or prior evidence. For example, if we deploy a new recommendation algorithm, CTR will improve by 5%. Simple. But designing an experiment properly is much harder than it looks. Because before running the test, we need to define several critical things. First, what's the minimum improvement we even care about detecting? This is called the minimum detectable effect, or MDE. For example, if a 0.2% improvement is meaningless for the business, there's no reason to design an experiment capable of detecting it. Then we define two types of statistical errors. Type 1 error, thinking an improvement exists when it actually doesn't. Basically a false alarm. Type 2 error, failing to detect a real improvement that actually exists. And here's the important part. All of these choices directly affect sample size. The smaller the improvement you want to detect, the more users you need. Detecting a massive 20% uplift is easy. Detecting a tiny 0.2% improvement may require millions of users. That's one of the reasons companies like Google and Netflix have such a huge advantage in experimentation. They have enormous amounts of traffic. After defining the hypothesis and sample size, we choose how to split users, define the statistical criteria, and even run simulation tests like A/A tests before launching the real experiment. And one of the most important rules in A/B testing is this. The experiment design is fixed before the test starts. You don't change the rules halfway through the experiment.
Assume we want to measure the impact of changing the purchase button color on customer conversion. The null hypothesis states that the change has no effect on conversions. We aim to detect a minimum uplift and want to determine the minimum sample size required to reliably detect such an effect. Another important parameter is the duration of the test. A common misconception is that experiments should run for a fixed number of days. In reality, experiment duration is driven by sample size, not time. To design a good experiment, we need to make a few key decisions up front. First, we define the minimum detectable effect, or MDE. This represents the smallest improvement that is actually meaningful for the business. If the effect is smaller than this, we don't really care about it. Imagine MDE is 2.5% in our experiment. Second, we consider the variability of the metric, or the standard deviation. This tells us how noisy our data is. The more variability we have, the harder it becomes to detect real changes. Let's imagine we are measuring revenue per user. In one scenario, most users spend around $10, maybe 9, 10, or 11. The values are very close to each other, so the variability is low. In another scenario, some users spend $0, while others spend $100 or even $200. Now, the variability is high. The third and fourth parameters are very important. Let's start with alpha. Alpha is the probability of concluding that an effect exists when in reality, it does not. In statistical terms, this is known as the false positive rate, or a type 1 error. In practice, we usually set alpha to 5%, meaning we accept a 5% chance of false alarms. Beta represents the probability of failing to detect a real effect when it actually exists. This is called the false negative rate, or a type 2 error. In practice, we often allow beta to be 10% or 20%. But instead of focusing on beta directly, we usually talk about statistical power, which is defined as 1 minus beta. Power tells us how often we successfully detect a real effect. In fact, power is exactly the same as the true positive rate, also known as recall. Now we want to calculate the required sample size. The formula for this is shown here. In this formula, S squared represents the variance of the metric, while the z-scores are obtained from the standard normal distribution, also known as the z-table. For typical values such as alpha equals 5% and beta equals 0.2, the corresponding z-scores are shown in the figure. Based on that, the formula for calculating sample size can be simplified as follows. As you can see, the more variability or noise we have in our data, the more samples we need. And the smaller the effect we want to detect, the more data is required as well. Now suppose the variance of our metric is 20, and our minimum detectable effect is 2.5, meaning that any change smaller than 2.5% in revenue is not meaningful for our business. Using the formula, we can estimate the required sample size. This gives us the number of users we need in each group, both for the control group and the treatment group. Also remember that before running an experiment, we usually use historical data to estimate the variance. Now the question is, how do we determine the duration of the experiment? If our website receives 20 users per day, we can simply divide the total required sample size by the daily traffic to estimate how many days the experiment needs to run. However, in practice, we usually don't expose all users to the new variation immediately. Instead, we gradually increase exposure. For example, 5% on day 1, 10% on day 2, and so on. This process is called a ramp-up. Additionally, user behavior often differs between weekdays and weekends. So in practice, we typically run experiments long enough to cover a full cycle, ensuring that we capture these variations in user behavior as well. In any experiment, we usually work with 3 types of metrics. First, key metrics. These are the most important ones, the metrics we actually want to improve. For example, revenue, click-through rate, or conversion rate. Second, control metrics. These should not change. If they do, it might indicate that something's wrong with the experiment. For example, page load time, or the number of users. And third, auxiliary metrics. These don't directly drive the decision, but they give us additional context. Things like time spent on the site or number of product views. The key takeaway is this: it's not just about one metric. A good experiment looks at the full picture. After defining the metrics, choosing the sample size, and designing the experiment, we finally launch the A/B test. Now imagine the experiment finishes, and we get the following result. The old system, Group A, has a CTR of 10%. The new system, Group B, has a CTR of 11%. At first glance, that looks great. But here's the real question. How do we know this improvement was actually caused by the new system and not just random noise? Because user behavior is naturally noisy. Some days users are more active. Traffic changes. Weekends behave differently. Marketing campaigns start. Random fluctuations happen all the time. So even if 2 systems were completely identical, their metrics would almost never be exactly the same. We must do an experiment. And this is exactly where statistical testing comes in. One of the most common tools is called the t-test. The intuition behind the t-test is actually very simple. It asks, is the observed difference large relative to the natural noise in the data? And mathematically, the t-score is calculated like this. T equals a difference between means divided by standard error. The numerator is easy. It's simply the difference between the 2 groups. The denominator is called standard error, or SE. Suppose our experiment produced the following data. Group A, mean CTR equals 10%. Standard deviation equals 1.2. Sample size equals 10,000 users. Group B. Mean CTR equals 11%. Standard deviation equals 1.1. Sample size equals 10,000 users. The observed difference is 11% minus 10% equals 1%. Also, by calculating standard error, we reach 0.0163. Now we calculate the t-score, which gives us t approximately equals 61. Now, once we calculate the t-score, the next question becomes, how do we go from this t-value to a p-value? The t-score tells us how large the observed difference is relative to the natural noise in the data. A small t-score means the difference is small compared to the uncertainty. A large t-score means the difference is huge compared to the uncertainty. Now imagine a bell-shaped distribution centered around 0. 0 represents the situation where there is actually no real difference between the two systems. Most random fluctuations naturally produce t-values close to 0. So once we calculate a t-score, we ask, if there were truly no real effect, how likely would it be to observe a t-value this extreme purely by chance? That probability is the p-value. Now technically, the t-score is compared against something called the t-distribution. And when the sample size becomes very large, the t-distribution becomes almost identical to the normal distribution, which is where the famous z-scores come from. That's why in large-scale A/B testing, people often talk about z-values and t-values almost interchangeably. For example, a z-score of about 1.96 corresponds to a p-value of 0.05, meaning only 5% of random experiments would produce a result that extreme if there were actually no real effect. So if our calculated t-score is larger than about 1.96, we usually consider the result statistically significant, meaning that we can reject the null hypothesis. However, this is only true under two important conditions. First, the sample size must be large enough, usually larger than 30, so that the t-distribution becomes approximately equal to the normal distribution. Second, this 1.96 threshold specifically corresponds to a two-tailed test with a significance level of alpha equals 0.05. If either of these conditions is not satisfied, we should use a t-distribution table to find the correct critical t-value instead of directly using 1.96. To do that, we first calculate 1 minus alpha. For example, if alpha equals 0.05 in a two-tailed test, then we look for the 0.95 column in the table. Next, we calculate the degrees of freedom, which is approximately df equals n1 plus n2 minus 2, which n1 and n2 are the number of samples in control and treatment groups. Then, using the corresponding row and column, we find the critical t-value and compare it against our calculated t-score.
Confidence intervals are crucial in A/B testing because statistical significance alone is not enough. A p-value tells us if an effect is real but not how large it probably is. Suppose we estimate an uplift of plus 2%. How certain are we about that number? Could it be 1.9, 2.1, or even negative? This uncertainty is captured by the confidence interval. We estimate a range of plausible values using the formula estimate plus or minus 1.96 times standard error. If our uplift is 2% and the standard error is 0.5%, the math is simple. The result is 2% plus or minus 1%, making our 95% confidence interval 1 to 3%. This means the true uplift is likely between 1 and 3%. That's the power of confidence intervals.
Now look at this funnel-shaped visualization. At the beginning of the experiment, the confidence interval is extremely wide. Why? Because we still have very little data, which means uncertainty is high. As more users enter the experiment, the standard error decreases, and the confidence interval becomes narrower and narrower. That's why the funnel slowly tightens over time. And this leads to one of the biggest mistakes in A/B testing: checking the experiment too early. At the beginning, the estimate is very unstable. One day, the uplift may appear to be plus 10%. The next day, it may drop to minus 2%. Early results are incredibly noisy. But as sample size grows, the estimate stabilizes, and the confidence interval shrinks. There is a very important connection between p-values and confidence intervals. If the confidence interval crosses 0, the result is not statistically significant. If the confidence interval stays completely above 0 or completely below 0, the result is statistically significant. And there is another important intuition. The farther the estimated effect is from zero, relative to its uncertainty, the smaller the p-value becomes. And that's why confidence intervals are often more informative than PE values alone. The final step is reporting result. Once the experiment is officially in the books, your job is to safely translate all that complex data into a format that company leadership can actually digest. This formal reporting table shows you exactly how to structure it. As you can see, we've got our metrics. Things like conversion rate and average order value, comparing Group A against Group B. We list the minimum detectable effect, the calculated lift, and of course, the all-important p-value. But I want you to look really closely at the conclusion column. If a result is significant, like we see in the top row, we don't just report one single point-wise effect. No, we estimate the confidence interval. We lay out the pessimistic lower bound, in this case plus 4.2%, and the optimistic upper bound of 6.9%. This gives leadership a crystal clear picture of how much confidence they can actually have in this result. And check out the second row. A p-value of 0.3704. That means there is no significant effect. And you have to report that completely honestly.
Thank you so much for staying with me throughout this video. So in this video, we explored the core ideas behind A/B testing completely intuitively. We talked about experiment design, hypotheses, metrics, MDE, type 1 and type 2 errors, and how sample size affects statistical power. After that, we broke down t-tests, z-scores, p-values, and statistical significance, and saw how the observed effect must be large relative to the natural noise in the data. We also explored confidence intervals, uplift monitoring, and why experiment results are extremely noisy at the beginning. And finally, we saw how to properly report A/B test results and honest statistical conclusions. If you found this helpful, please subscribe to the channel and share this video with anyone interested in data science or experimentation. Stay tuned for the next video.